Today, finishing up chapter 10.7, we're talking about or and probabilities, and we're talking about this idea of mutually exclusive events. So, first idea, let's talk about or probabilities where the events are mutually exclusive. Does anyone know what this phrase right here means, mutually exclusive events?
They affect each other.
They don't affect each other. They don't affect each other. Okay, mutually exclusive events mean they cannot happen at the same time. Okay, impossible to happen at the same time. All right. So I'm going to call this for short MEE for mutually exclusive events. And again, it means two things that cannot happen at the same time. Right. So if I say, throw a dart at a calendar, you can't hit two different days at the same time, even if you landed right on the line in between them, right? It would be one or the other. That's kind of a vague example, right? So if you're going to have a deck of cards, there's no way that you could pick the 15 of clubs because picking a 15 is impossible. And picking clubs is possible, but together it's impossible to happen at the same time. You could not pick a red spade. Okay, that's impossible. It can't happen. They're mutually exclusive. Does that make sense? So if the two things that cannot happen together, that's what mutually exclusive means. So here is our first part. So if we have two events, so if event A and event B are mutually exclusive events, and again, I'm just using MEE to abbreviate mutually exclusive events, then we have the following little formula here. So we say the probability of A or B happening, okay, A or B happening is just equal to the probability of A summed with the probability of B. So the thing that I want you to take away from this is that an or statement means addition. An or statement means addition, okay? Now, sometimes the book will use set notation, and the way to write this statement in set notation is the probability of A union B. I'm not going to use that notation. I would just type in the word or, but sometimes the book has the same thing. But it means exactly the same thing as this. Okay, here is an example. We're going to pick one card from the deck. We want to figure out the probability that that card is a king or a queen. The first question you want to ask yourself is whether or not these events are mutually exclusive. Are they mutually exclusive? Yeah. The answer is yes, they're mutually exclusive. They can't happen at the same time. If I'm picking one card, it can't be a king and a queen at the same time. So they're mutually exclusive. So given that fact, we say, okay, this is going to be the probability of a king summed with the probability of a queen. Now we have to ask ourselves, okay, what's the probability of getting a king? Well, how many kings are there? Well, there's 4, right? Because there's 52 cards in a deck, and there's 4 suits. Each suit has a king. So we have 4 out of 52. And we're going to add that with, what's the probability of getting a queen? Also the same thing, right? 4 out of 52. Now, the book gives all the answers in terms of fractions. So we'll reduce our fractions to the lowest term. So this would be 8 out of 52. Remember, when you add fractions, you just add the top 2 numbers if the denominators are the same. And that would reduce down to 2 out of 13. The book would give you that answer as a fraction in the back, okay? And your calculator can also give you that same answer. Did you know how to do that in your calculators, everybody?
To get fractions?
To get their fractions reduced to simplest terms? If you don't, I'm going to show you real quick right now how to do it. Okay, so let's say I take the number 8 and I divide it by the number 52, okay? And I hit enter. Calculator gives me a decimal, but if I want to convert this decimal to a fraction, it will always give me the lowest.
Bracket.
Yeah, so hit math. And then the first option you see is frac. So basically it says take my answer and make it a fraction, push enter twice, and then you get there's your 2/13, and that's what we got over there, the 2/13. So your calculator can help you out, assuming that your calculator is charged. Okay, here's another example. We're going to roll 1 die, okay? When we want to figure out the probability of getting a 4 or getting a 5. First of all, are those individual events, are they mutually exclusive? Yeah. They are, right? Because there's no way to get a 4 and a 5 on one single roll. So they're mutually exclusive events. So therefore, that implies that we're just going to take the probability of getting a 4 and sum it with the probability of getting a 5. So that would give us, let's see here, a 4. That is what, 1 out of 6, right?
Yep.
So 1 out of 6 plus another 1 out of 6 make 2 out of 6, which, of course, makes a third. And the book would probably leave it in terms of a fraction for you. Here we go. So let's talk about OR probabilities where they are not mutually exclusive events. So that means that they have overlap. Or that means that it is possible for them to happen at the same time. Okay? So the probability of A or B happening is equal to what it was before. It was just the probability of A plus the probability of B. But because these are not mutually exclusive, that means that it is possible for each individual event to happen together at the same time. If you think of a Venn diagram, right, you have the left circle and the right circle, and you have the overlap. Well, this is the overlap. It can happen at the same time. So we need to subtract the probability of them both happening at the same time, A and B. Now, I usually just call this both, because it's usually pretty simple to figure out. All right? So for these types of problems, this is what we're going to do. So here's another really important formula that we should be familiar with, and we use this formula when our OR probabilities are not mutually exclusive. Does that make sense? Okay, cool. Let's do an example. Okay, so example 4, we're going to draw one card from a deck, okay? So we're going to pick one card, okay? And I'm interested in the probability that that card is going to be a diamond or a face card. Okay, so do you see what I'm saying about overlap, right? Okay. Yeah, these are not mutually exclusive events. They're not mutually exclusive. That means that they could happen together at the same time, right? So there's going to be some overlap. So given the fact that they're not mutually exclusive events, I want to remind us that we're going to be using this formula, not the first formula, right? So here we go. So this is going to be considered as, we're going to figure out the probability of getting a diamond. We're going to add that to the probability of getting a face card. But then what do we have to do, everybody?
Subtract the both.
We have to subtract the probability that they happen together. Both, right? Both means diamond and face card. Okay, so let's figure out their individual probabilities. What's the probability of getting a diamond?
1/4.
Yeah, I'm going to keep it in terms of our common denominator of 52s, right? So there's 13 cards per suit. And there's, of course, 4 suits. So this is going to be 13 out of 52. That's a probability of just getting a diamond, right? Which, of course, Michael, as you said, is 1/4, okay? Now, probability of getting a face.
There's 4.
Well, what's a face card again? Let's remind ourselves what a face card is. A jack, a queen, and a king. Joker doesn't count, and ace doesn't count. So there's 12.
52s.
So we're going to add this. There are 12 52s out of this one, right? Okay, now we have to subtract off the fact that, well, there are face cards that are diamonds, right? Because this is not mutually exclusive. So how many face cards are diamonds? 3 of them, right? You have the jack of diamonds, the king of diamonds, and the queen of diamonds. That makes up our 3. So we need to subtract off the overlap of 52, 3 out of 52. So together, collectively, that makes
22 50-seconds.
22 out of 52.
11.
Which, of course, makes 11 out of 26. All right, 11 out of 26. Okay, so let's take a look at this spinner question. I've got a spinner here. I'm interested in the probability of getting an even number or a number that is less than 4. So yeah, so they are not mutually exclusive events, right? These are not M-E-E. The reason being, there are numbers that are even and smaller than 4, so we have to consider that overlap, all right? So we're going to go ahead, all right, let's figure out the probability of even. And then we're going to add that, the probability of a number less than 4. And then we're going to subtract off what? Who's got it for me? Subtract off what?
Oh, we're going to subtract off the even numbers that are less than 4.
You got it, the even numbers that are less than 4, so both of them. Okay, help me out. What is the probability of getting an even number? Let's circle them. Well, there's that one, there's this one, and this one. So what would that be?
4/8.
That'd be 4/8, right? Okay, what's the probability of a number less than 4? Well, there's 1, 2, and 3 of those, right? So there's 3 of 8 of those. And let's subtract off the double. How many are less than 4 and at the same time even?
1.
Oh, it's 1, just the number 2, right? So let's subtract 1 of 8 from that one. So I had 4 and 3 make the 7, right? So this minus the 1, so what does that give me?
6/8.
6 out of 8. which is just 3/4, right? Multiplied, reduced down to 3/4. Okay, box 6 is the and probabilities types of questions. And we're talking about with independent events. IND period. This means independent events. So what does that actually mean? What is the definition of independent events?
It's the opposite, or it's like, oh, they're just not even happening together. They're not even related.
Yeah, it's when
They're
one.
not related.
Well, it's when one event does not have an effect on the other event. So, like, if I flip a coin twice,
It's not gonna
They
be
don't
okay.
affect each other.
the first one has no real bearing on the second one. That's what independent events means, right? So if I'm trying to calculate the probability of A and then B happening, right? So these are two separate events and they're independent. Well, then I just multiply those probabilities together. So that's probability of A multiplied with probability of B. So the word and means multiply. So I put a little X by that. It means multiply. It would be nice if the word and meant add because there's an A in each of those words, but it doesn't. So this is the third and final pretty important formula that we want to be sure that we're familiar with, okay? So as an example of this one, I'll just do it right here below it. We're going to roll a single die 2 times. We're going to roll a die 2 times. Okay? So what I'm interested in is, what is the probability of getting an odd, and then,
This was number 46.
exactly, a number that's less than 3. That's a less than sign. Number that's less than 3. All right?
So does that mean the probability of getting an odd for your first one?
Yeah, probability of getting odd for the first roll, and then a number that's less than 3 for the second roll. Okay? So, yeah, they're not together. There's 2 rolls. Right? I'm rolling one die 2 times, right? Okay, so does the first roll have any effect on the second roll? No, so that makes them independent events. So therefore, we find this by just multiplying their individual events. So the probability of odd multiply with the probability of a number less than 3. Well, the probability of odd is, of course, half of it, so 3/6. And the probability of a number less than 3 is 2/6. Because I'm just getting either 1 or 2, right? So the probability of those things happening together successively, it is going to be the product of those two things. So it would be 6 out of 36. Right? You guys go with that? Which is, of course, is just 1/6. And that would be the way that we represent the answer.